Welcome back, everybody. Again, apologies for Friday. I think we're on track. I was comparing to what I've done in previous years, and I think that extra day that I was thinking about giving you guys off, I think I just gave it. So it was, you know, a built-in sick day. So good news is we have just one more week before break. So I'll be giving you another homework on model selection, but I'm not prepared to give it to you yet. I almost certainly am not going to give it to you over break. But what I might do, if we can get to it this week, is I'll try to give you a couple extra credit problems and tell you how some of this stuff extends to more sophisticated problems and give you an opportunity to verify or compare some Bayesian analyses against non-Bayesian analyses. So it's one thing to understand the asymptotics and the mathematical argument, but it's another thing to actually demonstrate this stuff in reality. How does it actually work? So I'll be giving you a lot of problems on that. There's a zillion ways to do model selection, so I'm going to try to tell you about a half a zillion ways and do some comparisons. The nice thing is there's a lot of built-in facilities for doing things, and you're going to be allowed to use some software to do the problems, but there will be an MCMC exercise that I'll be asking you to code up as well. So that's just kind of a roadmap of where we're going. I want to introduce you to a couple papers. So you can review this. We'll be going over this paper a little bit later today, but this is about the interval test. And so Mark Shervish over at Carnegie Mellon University wrote this paper some time ago titled P-values, What They Are and What They Are Not. So the what they are not is they're not a measure, and we've already stated that. And so what is a p-value? If a p-value ducks alpha, and alpha is, let's just use the typical number, 0.05, what does that mean? So if somebody says, I got a p-value and I got a pre-specified alpha, and that's critical to pre-specify your alpha, and the p was ducked alpha, should you even care what the p is? Neyman and Pearson say no. Fisher says yes. Fisher's wrong. So unfortunately, in some cases, maybe the size of the p-value does mean something. In the one-sided case, the Bayesian computes a posterior probability, and that posterior probability coincides with the p-value. So in that sense, it's a measure. And so I sympathize with Fisher, but Fisher was being inconsistent about what he was advocating. And so he knew through some examples things worked out a particular way, but it wasn't general enough that he could use the p-value as an actual measure. And this paper will help to explain that. What it means is that your type 1 error rate, if the null is true and you reject it, the type 1 error rate is that alpha level. So it's alpha, it's 0.05. So the error rate of rejecting the null hypothesis incorrectly is 0.05. Also, if you're doing the Neyman-Pearsonian thing where you're thresholding using a likelihood ratio test, and I don't go through all those details. So if you're realizing you're missing the details on it, you need my inference class that I teach. So Stat 5114, I go through all the details on why when the likelihood ratio is thresholded by some constant, that's a uniformly most powerful test. What it means is that the type 2 error rate is minimized. So the type 2 error rate is if the alternative is true and I don't reject the null, I've just made a mistake. So that's the typical language. So that's the other type of error. So one of two things can be true, so you can make an error on both sides. The type 1 error rate is fixed at alpha, and the type 2 error rate is minimized. And you would have to compute what the type 2 error rate is for various values of the distance away from the null hypothesis. And if you've taken a full-blown inference class, you'll understand that as the power curve. So, and that power curve is as big as it can be. So the type 2 error rate is 1 minus the power. You can think of it that way. It's not exactly true, but that's the way we usually use it. So again, the Neyman-Pearsonian thing, they're not building a measure. The p-value that you end up getting, it's controlling error rates. So it's got a fixed type 1 error rate if you pre-specify alpha, and it has a minimized type 2 error rate. So it's not a measure of the null hypothesis itself, it's a statement about a procedure. And it's a frequentist procedure that if you kept rerunning it over and over again and you check to see what your error rates are, your error rate should be 0.05 for the type 1 error rate, and the type 2 error rate is minimal. So if you used a different test statistic than the one you would get from the likelihood ratio, you would have a greater type 2 error rate. So that's the idea, and that's what Mark Shervish kind of explains. What he wants to talk about in this paper is the interval test and show you some surprising results. So the interval test is just testing this. H naught, theta is equal to theta naught. Oops, I don't know why I did that. Theta is an element, I'll say theta 1, theta 2. And the alternative is theta is not an element of that interval. Theta 1. So it's outside of this interval. And so that's what we want to consider. We might consider an example. So from Shervish's paper, his example looks like this. Is X is going to come from a normal distribution with mean mu. So you could call that theta if you want. And it's going to have some known variance. And so they're going to tell you that the variance is new. If it is known, and they're going to specify it to be 1. Just keep in mind that if you didn't know the variance, you would use a t distribution instead of a z distribution. And a Bayesian would do that as well, for slightly different reasons, but the math is exactly the same. So the typical test statistic that you would normally use for testing something, this is just one data point, but because we know the variance, one data point is enough to infer what the mean is. And so if you had more data points, you would use x bar, and then your variance would get scaled by n. So your variance would be 1 over n. Your standard deviation would be 1 over square root of n. And so having more data points doesn't like generalize anything for us. So this is a perfectly general example. And so if you did have more data points, exactly the same thing would work out. And if you didn't know the variance and you used a t distribution, exactly the same stuff that Mark Shervish demonstrates would also happen. And so there's nothing cheeky about this choice right here. This is a perfectly general example. And they're going to just try to figure out what is the p-value associated with this hypothesis test. So I'll write it this way: mu1, mu2 is going to be our interval that we're testing, and the p-value is going to depend on this data point right here. And so what Mark Shervish does is he recycles a result from Eric Lehman. I don't have any relationship to Eric Lehman, it just seems to be spelled the same, but Eric's name has an H in it. So he's the one that wrote that hardcore inference book back in the 60s, 70s that some people still use. He came up with the uniformly most powerful test for testing this. So the way he came up with the test is he used the likelihood ratio and thresholded it by k. So he's coming up with that same exact procedure, and if you're familiar with the proof in Neyman Pearson, everything works out the same as all those examples that you've done in Stat 5114. And if you want to know more about all that stuff and you haven't been introduced to it, Stat 5114 is your class. So basically they're able to derive the p-value. And so Eric Lehman did this a long time ago. And that p-value is described right here. So he writes it down for us. I'm going to rewrite this for us, but it's just this thing, and I'll try to explain it just real quickly, what this p-value actually is telling us. It's notes. So this symbol is the cumulative CDF function right here. I'll give myself just a little bit more room because I'm going to draw some pictures in a second. So x comes from a normal mu1. So this is the normal CDF. It's just a cumulative normal function, the same notation that we've been using since Stat 101. So this looks like x minus mu1 plus cap CDF x minus mu2. And this has a condition. This is if x is less than mu1 plus mu2 over 2. So this is just the average. I'll call that mu bar if you want. And all this stuff gets flipped around, mu1 minus x if the other condition is true. Mu2 minus x if x is greater or equal to mu bar. It doesn't matter where you put the equal sign. You could put it in anywhere. This is a continuum, so it doesn't matter. So measure 0 at that point. So let's just think about what this is actually saying for this test right here. This might be a little bit counterintuitive, but we'll try to build some intuition. Again, how did Eric Lehman derive this? He used the likelihood ratio test statistic, and he thresholded it. And this is the most powerful test. Let's just think about these test statistics right here, x minus mu1. Where's that coming from? That's pretty intuitive. That's like using x bar minus mu divided by the standard error. Sigma squared divided by n. Or, sorry, sigma divided by square root of n. So our sigma is 1, and we have 1 data point. So that's what that looks like. This is that x bar thing minus the hypothesized value divided by the standard error. Standard error is 1. So these test statistics look like the right thing. And so saying that, I do follow Neyman Pearson when I'm doing things to make sure I'm operating with the right test statistic. So I'm modeling things in the most powerful way. So there is good Bayesian stuff you can conjure out of that Neyman Pearsonian stuff. So just not the sharp thresholding of everything. That's where Bayesian might disagree. So let's just think about what this looks like right here. So this is saying I've got some interval mu1, mu2, and my question is true mu in here? So versus, is it somewhere else? And so there's some average to this. We'll call that mu bar. And if this condition is true, right here, x is somewhere over here. X is over here or farther back. So it's not over here, that's this other condition. So let's just think about what these cumulative normals are actually measuring in the first place. So x minus mu1, x could be, this thing could be positive or it could be negative. I'm going to draw the picture so that it's like in here, so it's a little bit positive over here. So if I just think about this cumulative normal, this is centered at 0 right here. And I'm going to be imagining that x is bigger than mu1, but it's less than mu bar. And so this is going to be this area right here. So this is something positive. If x was going over here, it would still be less than x bar, and this little line right here would be pushing back right here. So it'd be getting smaller and smaller. And so if I think about the relationship between x and mu1, is what this is actually measuring is just how close is x to mu1. And that's ultimately what this is measuring. Is it close to that endpoint? So if this x is way down there on the chalkboard, this is going to be negligible. So x isn't going to be very close to mu1. If I think about this right here, x minus mu2, mu2 is bigger than x, that's guaranteed, because mu2 is bigger than mu bar, and x is less than mu bar. And so this is just another cumulative normal, the thing centered at 0, and it's this tail probability over here. So what this is doing is this is measuring how close you are to mu2. And we could draw a similar picture over here. If this condition is true, this would be the bigger probability, probably this one, and then this one would probably be the smaller one. So ultimately what this test is testing is how close you are to these two endpoints. How close is x to the endpoints itself? So it seems like, okay, I guess that makes sense. If you also notice, if we ended up taking the limit of all of this, so let me just change this to the mu's. So let's just say mu is an element of this interval. Just to use the same notation, mu's not an element of the interval. Is the alternative. If I think about the interval hypothesis test and I take the limit and I push, let's say mu1 to negative infinity, what I'm going to be doing is doing the one-sided test. And so if I push that all the way to negative infinity, these things right here are going to go to 0. So let's just think about if mu1 went all the way off to, let's take that one right there. If mu1 went all the way off to negative infinity, this is going to be vacuously small. So it's going to go down to 0. So this part would be left out, and I would just be left with this part right here. And so this is the one-sided test where you just use one cumulative normal to do the one-sided test. Same thing happens if mu2 went off to infinity. We would have the other direction of the one-sided test. If mu1 and mu2 went to each other and they collapsed to each other, that would be the point null test. So mu1 and mu2 converge to the same thing. Let's just think about what happens here. mu1 and mu2 converge to the same thing. I would call that maybe mu naught. And I'd be adding together these identical cumulative normals. And that would be the 2 times factor that we studied last week. So the sharp test had a p-value that was twice as big as the one-sided test. And we kind of talked about that as being incoherent. That doesn't quite make any sense because the null space is tiny compared to what happens in the one-sided test. But you would get that 2p factor from this. So the limit of this test in terms of the one-sided test and the point null test, it's exactly the same stuff they teach you in Stat 101. So this is a generalization of that. You've probably never seen this thing before. And the reason why is because terrible things happen with it. So again, Naiman and Pearson are correct. It's still the uniformly most powerful thing, if that's something that's meaningful to you, with a fixed type 1 error rate. But let's just consider some numbers real quickly. So I've computed this already. Done some pre-computing, make sure I've got some examples. These examples come straight from the paper, so you can read through the paper. I think those examples appear down here. So let's just look at those numbers. I'll just hide those for a second. See what we think about everything. Let's consider this test. So here's our first test, test 1. Let's consider our p-value, where I'm testing if mu1 is minus 0.5 and mu2 is 0.5. And let's say I see an x of 2.18. Where did Mark Shervish come up with these numbers? We'll see in just a second where he probably engineered these numbers. The minus 0.5 to 0.5 is probably arbitrary. He probably picked this number so something amazing happens. So let's just compute that thing. Make sure there's no numerical problems in Shervish's paper. So norm CDF. So this is that same function. You can check real quickly that I've done this in the right order, but it's this one. So you ended up checking these values. What's mu bar at 0? And this thing is greater than 0. So this would be the version of the test we would use. So I've computed that right here. So norm CDF minus 0.5 minus x. Oh, and I've also already inputted what x was. So let's just make sure. X is 2.18. Norm CDF. Plug in those exact same numbers. And we come up with something, 0.052. So where did he come up with this 2.18? He wanted to push that thing close to 0.052 so he can make another point. So this thing is 0.052. Okay, so do you reject or fail to reject on this? I get Fisher's point, you know? So why not think about this continuously? But Naiman and Pearson say, hey, if you want to make this some sort of interpretable probability, you know, maybe we can talk about error rates, something like that. So Naiman and Pearson were saying Fisher was over-interpreting the p-value. So that's 0.052. Let's consider another couple tests. So let's think about test 2. Let's test mu is an element of minus 0.5 to 0.52. So what I've done is I've taken minus 0.5, and I've bunched this thing to the right just a little bit. So I've made the set bigger. So what do you think? Should the p-value get bigger or smaller? Like, what do you think should happen if the p-value was a measure of evidence and it could be considered an actual measure? If I make the set bigger, should the p-value get bigger or smaller? You'll have to think about this for just a second. What would you like it to do? Bigger or smaller? Take the limit of this. Make the set huge. Negative infinity to infinity. So what would you like the p-value to be? Big. 1. So I wouldn't want to reject that sort of thing. So if I had negative infinity to infinity, and you can check this thing out, then it will be 1. So it does something right in the limit. So, but if I were trying to test is mu between negative infinity and infinity, and there was my model, I wouldn't want to reject that. And this test wouldn't reject that. You would get a p-value of 1 in all these cases. I'll let you just do the limit and rethink about these pictures just a little bit. So one of those p-values would go to 0 and the other one would go to 1. Or sorry, one of these cumulative normals would go to 0 and the other one would go to 1. So we want it to probably get bigger. What do you think? Anybody still want to argue smaller? Okay. You can go back in videos if you would like. I usually poll the class and it's usually divided. But I've been a little bit too leading in this conversation, I think. But let's just check this out. Norm, CDF, make that a 0.52. Boom, 0.05 to 1. Can ignore that. So I need to update my license. Sorry about that. So 0.0521. So it did get bigger. So that's pretty cool. So it seems to work okay. So the p-value from minus 0.5 to 0.52, 2.18 is equal to 0.0521. Do I have that right? Yeah. So this is bigger. That seems good. So at least the way I've rationalized it. If you think like a Bayesian, what would happen if you increase the interval length? And you're completely subsuming the old interval. It would get bigger. So you'd be integrating over more mass in the posterior probability. So let's think about something just a little bit different. And let's do this other test of minus 0.82 to 0.52. So let's consider this one, test 3. And compute the p-value minus 0.82 to 0.52. So what I've done is I bunched this thing to the 0.52. Right there, I kept that the same. And then I started budging this one over to the left, minus 0.82. Well, we want to compute this p-value. What do you think? Should this get bigger or smaller? I would think bigger. So if this were a measure, I would think it should get bigger. Lo and behold, that doesn't happen. This is 0.0498. 0.0498. This is smaller. Regardless of who you are, if you thought this was a measure of support for the null hypothesis, we might be confused. Maybe we've confused ourselves whether or not it should get bigger or smaller. I'd say if the interval is getting bigger and subsuming the old interval, if it were a real measure, it should only get bigger. But definitely it shouldn't get bigger and then smaller if I keep budging this thing. It doesn't make any sense. So this is non-monotonic. This is what people call is non-additivity. So we're not adding up the space. It doesn't have an additive property. And you'll hear Bayesian say, this is the incoherency problem. So interpreting a p-value as a measure of support is incoherent. And this example shows the incoherency. And so they probably don't show us this example in Stat 101 because we'd all be like, is this just total nonsense? So if you tried to use that game where you said, oh, I'm looking for contradictory evidence, and I've got this measure of contradictory evidence, you know, your data and more extreme data, and you use that argument in Stat 101, it would break down on this example. And so anyway, just think about what a Bayesian would do. If a Bayesian computes some number for this test, and punch the interval to the right, the posterior probability on the null would get a little bit bigger. And if I budged the lower limit to the left, the posterior probability would get even bigger. And so that's additive. We're able to add those probabilities together. And that's what we call coherency. So Bayesian is actually giving you an additive measure. Okay, if you'd like to read through that paper or cite it in the future, it's an oldie, but it's a goodie. So I'd encourage you to just at least skim through it. Any questions about all that? Okay, the conversation gets a little bit worse. So let's look at a few other readings that I've given you on the web page. So people have been hassling each other about p-values for a really long time. And this is certainly not the first time you've heard there's some issue with these things. The issue is interpreting them as measures. They're not that. So if you do an experimental design, if you go out and you collect the right amount of data so that your power is at some reasonable level, so you can test at some distance away from your null hypothesis, you fix it and you go collect that data, and then you control your error rates, you pre-specify alpha, you compute your p-value. If it ducks alpha, you reject. I think that that's a reasonable setup if you really want to control error rates. But just in general, using these things in observational studies, I don't think makes a whole lot of sense. Pertaining to that, the journal Basic and Applied Social Psychology has decided to ban p-values. So I may have shown you this in my inference class, but it's worth reading just again. You can read through this if you'd like. This is also on the web page. So let me just read to you a couple paragraphs here. The Basic and Applied Social Psychology, that's BASP for short, 2014 editorial emphasized that the null hypothesis significance testing procedure, that's Neyman Pearson. So if the likelihood ratio ducks some threshold, you reject. And you calibrate that to error rate. So that's what they mean by the null hypothesis significance testing procedure, the Neyman Pearsonian thing, is invalid. So let's just read that again. Basic and Applied, so BASP 2014 editorial emphasized that the null hypothesis significance testing procedure is invalid and thus authors would not be required to perform it. Does anybody know who this person is? He's the editor that said that. So he's also the one that's writing this statement. So he's citing himself. However, to allow authors a grace period, the editorial stopped short of actually banning the Neyman-Pearsonian procedure. The purpose of the present editorial is to announce that this grace period is over. From now on, BASP is banning Neyman-Pearson. With the banning of Neyman-Pearson from BASP, what are the implications for authors? The following are anticipated questions and their corresponding answers. So, will manuscripts with p-values be desk rejected automatically? They say no, but they're going to ask you to remove it before publication. So no, if manuscripts pass the preliminary inspection, they'll be sent out for review, but prior to publication, authors will have to remove all vestiges of name and Pearson. P-values, F-values, all that stuff. What about other types of inferential statistics such as confidence intervals or Bayesian methods? Answer to question 2, confidence intervals suffer from an inverse inference problem that is not very different from that suffered by the name and Pearson thing. So they've got a one-to-one correspondence with each other. And some of you will understand that. So you can read through that. I think what they say over here, Bayesian procedures are more interesting. I love that. So it's not really an argument at all. So, but they say you're allowed to be Bayesian, but you're going to have to justify your priors and things like that. That's a strong statement. So I think that in some cases, doing the p-value thing and thresholding might be valid. I described the basic setup that Naiman and Pearson described in the way they proposed it. But here's what's going on in things like BASP or in social psychology. Does anybody know how most research looks in that field? So grad student, if you know any grad students and they're writing a PhD thesis, I almost guarantee they're doing this one thing. They're writing a survey and sending it out to hundreds of thousands of people. And you get those surveys all the time in your email box. I get them all the time. Please spend 15 minutes, we'll give you $1. Delete. So response biases mess everything up in those sort of setups. So you're only going to get people that feel most afflicted by something, so you're going to get the strongest opinions. But also, whatever they're testing is almost certainly not true, which is why they're testing it in the first place. And they go out and they just get some N that's big, 100,000 people, I'm just going to send out this survey until my p-value is tiny. And so with N being big, probably their model is not right that they're presupposing. Keep in mind they're dealing with people that don't act like, we don't do the IID thing. So it's not IID in the first place. So probably what they're rejecting is their IID assumptions. And maybe not even their hypothesis, but it would be more compelling if they showed us what are the differences between two groups instead of just saying the groups are different. That's not very illuminating. So I think for their field, this makes a lot of sense, but it might be a bit of an overreach for all fields. ASA decided to comment on this, so they woke up. So this is the American Statistical Association, and said, well, if other people are saying things, we better say some stuff. And so this manuscript addresses that. There is a follow-up manuscript to what the ASA said. They broke out into 2 different committees, the Bayesian Committee and the Frequentist Committee, and they advocated, and nothing changed. So the Bayesians ended up saying if you must use a p-value, just make alpha smaller. So they said maybe you could just take 0.05 and turn it into 0.01. That's not that solves nothing. So I did go to a few people on that commission. I asked them, how could this be what you ended up coming up with? And every single one of them told me, nobody agreed with this. This was the closest we could come to some form of agreement. So still the field is in limbo with what we should do. The purpose of my lectures are just to point out what some of the issues are. Again, I'll tell you what I would normally do, but usually what I do is I do predictive analyses and I do estimation. I try to explain what the differences between groups are, and I avoid point null testing. There'll be more commentary on that later. Is this a surprise to anybody? Not a surprise. Okay. This is borderline embarrassing. So I would say I don't do this sort of thing, but again, I think for the interval test, I kind of see it as a super reasonable test. I wish more people were talking about that test, talking about their actual limits, and then computing measures that are coherent. And if you're a Bayesian, I think that that's a reasonable thing to do. Let's go back to the Sharp test and work out what a Bayesian actually does. Sam had asked me an interesting question over before the weekend, and he said, it's really weird to me that we use different priors when we're testing different things. And I want to come back to that question. I don't want to answer that whole question, but I'm going to try to answer it through an example. So let's just go through an example and see what happens if we did use the flat prior on the point null test. But let's just construct this from scratch. Bayesian sharp testing. So we're going to test something like this. We want to test that, and let's do xi's come from a normal, so that we can compare this to what we've done in our classical statistics classes. So I'll say this has variance sigma squared. So I've got n IID replicates. So everything's IID here, and I want to test this. Okay. So here's what a Bayesian does. First thing, we know what the likelihood is for everything because we've specified the sampling distribution. We need some priors. So last time we advocated the point mass mixture prior. We'll come back around to discuss this choice and discuss why we have to do something like this if we want to test this hypothesis, and why this prior is different from the ones that we used for inference. I'm almost glad that this bothers you. So saying that, let's just work through the example and see what the issues are. This does have a name. It's called the Bartlett-Lindley paradox. So this sort of thing that you're grappling with, other people have grappled with as well. I'll tell you what they've said. So point mass mixture prior looks something like this. This is always true, that it's going to be some mixture if I'm testing two hypotheses, but I'm going to write this down as pi naught times the delta function that theta is equal to theta naught. That's what we're calling the null prior. So that's the prior on the null space. Plus, I've got some mass on the alternative space. So this is the probability that the alternative is true a priori, how much weight I'm putting on it. And then I have the alternative prior. So H1 over theta. And what we decided last time is we were going to work with the conjugate prior. So we'd take this to be normal, we'd center it at theta naught, and we'd have some variance in here. And I'm going to call that variance psi squared. And what I've already pointed out, and we'll point out through this example, this is extremely important, how you pick it. Ultimately, what we're going to say when we work out all the math is that that's going to calibrate the distance you need to be from the null hypothesis before you're willing to reject it. If I just think about, if I used a flat prior right here, this looks like this, psi naught, theta naught, and this is my distance, my variance right here. If I ended up making psi squared really, really big, it's going to flatten this distribution, push mass out into the tails farther and farther. And if you just think about conceptually for a minute, how much weight we're putting on each point in the alternative space when we diffuse it a lot, we're putting less and less mass on every point in the alternative space. But we're keeping this mass on the null space always the same. So ultimately, because this is a comparative analysis, what we end up doing is we put much more mass on the null space. Let's work through the math so that we can see all those details. So what we need to do first, if we're going to use this point mass mixture prior, is we probably need to work through the Bayes factor. So let's see how far we can get on that. So our Bayes factor is just this thing. This is always true. This is going to be the integral. Theta is in the null space. I'm going to take, I could call it likelihood function, or I could put sampling distribution in there. It doesn't really matter because they're the same up to proportionality, and all the integrating constants will cancel each other in the numerator and the denominator. So I'll just write it down like this. Same notation that we've been using the whole time. But I could have replaced that with likelihood. And a lot of people do write that down. There's my prior on the null space. I'll use the same notation that we used before, P, d theta. And this is going to be the integration over the alternative space. D theta. So let's just replace some stuff. Plug in what we know. So this is going to be the integral. Theta is an element of the null. Right here. This is going to look like 1 over 2 pi, if you will. Square root 2 pi, those will cancel. That's not important. This will be sigma over root n. E to the minus 1/2 x bar minus theta squared over sigma squared over n. And then I've got my null prior. What's the null prior? It's this point mass. D theta divided by a similar integral. E to the minus, should be exactly the same thing. Sigma over root n, e to the minus 1/2, x bar minus theta, squared over sigma squared over n. And then I've got my alternative prior. And I'm saying that's conjugate. I'll plug in all the normalizing constants if you'd like. Square root 2 pi psi, e to the minus 1/2 theta minus theta naught squared over psi squared d theta. So this is going to be theta in the alternative space. What's the alternative space look like? Minus infinity to infinity. You can remove this 1 point theta naught if you would like from this integral, but it won't change the value of that integral. So I never put in the actual indicator function saying theta naught's not in that set. But if you like it in there and you like to write it down and it helps you to think about it, you could write that down. So it just doesn't matter if you remove a point from everything. And so let's chisel away at the top integral. It's probably the easiest part. So when I integrate over all of, if I wanted to integrate over all of theta, it only takes on a positive value right here. But I'm only integrating in that 1 point right here. All other points other than theta naught, this thing is a 0. And so at theta naught, that takes on an actual positive value. And so as I integrate across this, this is only positive at 1 point. And so that's the easiest integral in the world to work through. Base factor is going to be this thing on top in the numerator, sigma over root n, e to the minus 1/2 x bar minus theta naught. That's my one positive value in all of this, sigma squared over n. So I just plug in this one value that has some positive mass on it right in here. So all I'm doing with this integral is just plugging theta naught right in there. So again, the easiest integral in the world to take. The bottom one is a little bit harder. So I'm going to write it out like this. This is px bar. So px bar is just the margin of the data. So the way I've written all of this down, I've got my data right here. Instead of using all of my data points, I've replaced everything with x bar because x bar is sufficient for data. So the mean of the distribution. So I've just worked with the sampling distribution for x bar. If that confuses you, you could take that product to form the likelihood and everything would work out exactly the same. They're the same up to proportionality. So I'm doing kind of a shortcut and just recycling things I know about inference. So that x bar is right there. So when I'm integrating across theta, I'm marginalizing out theta. So this is just a function of x bar down here. It also has something to do with sigma squared and the psi squared and the theta naught. We probably need to work through that. So I think next time what I'm going to do is I'm going to work through this integral right here. And I'm going to write it up on the board so that we don't have to spend 15 minutes doing all the steps. But what you'll need to do this integral is you'll just need to factorize all the stuff out that doesn't have something to do with theta, bring it out in front, right here, and then you're going to complete the square. And you're going to figure out what all this is. But you can see automatically if I expand this part, the square, I'm going to have an x bar squared term right here that I can pull outside of the integral. So you can convince yourself instantly, because this is e to the minus x squared, e to the minus some quadratic form in the random variable. The random variable here is x bar. That's going to be a normal distribution. I'll just point out real quickly which normal it is, and then I'll write down all the steps of the integral next time. So I'll come in 15 minutes early and go through that. And then I'll erase it so that it's at least in your video. But this is going to be a normal distribution. Does anybody know where it's centered? I've certainly said a couple times. But I don't know if we've worked through every detail of this integral. It's centered at theta naught. Does anybody know what the variance is? It's going to be sigma squared over n plus psi squared. So if we work through this integration and we complete the square, that's what we'll come up with. So I'll fill in those details next time. So this part right here is just going to be some other normal. 1 over root 2 pi. This is going to be sigma over sigma squared over n plus psi squared. And I'm going to take the square root of that. E to the minus 1/2. This is going to be x bar. It's going to be centered at theta naught squared over sigma squared over n plus psi squared. So that's what this Bayes factor is going to look like. What I'd like to do next time is simplify this a little bit. So and just write down again where we got this from, and then I'm going to write this in a slightly different form where I don't just have 2 exponentials, but I have just 1 exponential. We'll come back next time, simplify that a little bit, derive where this came from, and then we'll start analyzing the dependency on psi squared and everything else. And we'll show how this corresponds to the posterior probability, and then we can maybe address Sam's question of none of this makes any sense. So we'll see where the paradox is. Just as a heads up, there's no actual paradox, there's just confusions. I'll try to deconfuse everything. That's it for now, you guys. So next time we'll try to work through this example, and then hopefully on Friday I'll be able to give you some prelude to some extra credit.